Welcome to Spring LIB.
Okay, so here we need to assume we need to find a formula for the net force. So we can assume we could assume that the net force would be equal to negative kx minus cv squared, and this is equaling the mass times acceleration. However, here the damping force would always be in the negative direction, since cv squared would always be greater than or equal to 0. So because the damping force is not always in the negative direction, we need to model a damping force that is in the opposite direction of the velocity at all times. So although we're using this as a model, we can't use this equation. So the new net force, given that the damping force is always in the opposite direction of the velocity, the new net force would be equal to negative kx minus cv times the absolute value of the velocity, and this is equal the max. This would equal the mass times acceleration. So the acceleration would be equal to negative kx over m minus cv, absolute value of v, divided by m. And at this point, we know that from equation 14.5 that x, the initial position of x will equal x naught. In this case, will equal negative 0.100 meters. So we can say that a naught would be equal to negative kx naught divided by m minus cv naught times this absolute value of the initial velocity divided by the mass. We need to assume the acceleration was constant over the next time interval. So here x sub 1 would be equal to x naught plus v naught delta t. We're simply using a linear translational kinematics at this point. A naught delta t squared. And then a naught, you are to substitute this into your a naught. Oh, my apologies. So from this, we can then say v sub 1 equals v sub 0 plus a sub 0 delta t. Therefore, a sub 1 would be equal to negative kx sub 1 divided by m minus c v sub 1 times the absolute value of v sub 1 divided by m, and it just keeps on going for every successive interval. So we need to apply this method for a time interval of 0.01 seconds, 0.005 seconds, 0.001 seconds, and then 0.0005 seconds. And this is because we need the results for position, velocity, and acceleration. These must agree within 2% between the results for that interval and the interval before it. So if you want to see what this would look like, these would be the values. So these would be the numeric values of each of the different time intervals here. And the 2% agreement occurs right here. So these two time intervals all results agree within 2%. So that's why we have to stop at 0.001 second and 0.0005 seconds. And then if you wanted to see the graph for the position, this would be the position versus time graph. This would be the velocity versus time graph. And then this would be the acceleration versus time graph. As you can see that the velocity versus time graph is simply a derivative of the position versus time graph, and the acceleration versus time graph is simply a derivative of the velocity versus time graph. So you can use any sort of graphing software in order to obtain these graphs. That is the end of the solution. Thank you for watching.